So, you are sitting there comfortably in your armchair while watching your favorite TV show, just sitting still and doing nothing, just relaxing and enjoying your beautiful life. Just sitting still, not moving at all. But are you so sure you're not moving at all? I mean, have you ever considered that when you are sitting or standing still, you're actually moving? And pretty fast, by the way. Yeah, I'm sure you're asking now. How come? Well, any answer will be incomplete unless you know first what's actually the meaning of speed. Speed is equal to the distance traveled over the time taken to travel that distance. For example, when your car is moving at 50 miles per hour, it means you cover the distance of 50 miles per each hour you're traveling. So if you move at that same speed for 3 hours, you will cover the total distance of 150 miles. In most countries, however, they measure speed in kilometers per hour, so the same example goes like this. If a car is moving at 80 kilometers per hour, it means you cover a distance of 80 kilometers per each hour you're traveling. So if you move at a constant speed for 3 hours, you will cover the total distance of 240 kilometers. However, in science, we don't measure speed using neither miles nor kilometers or even hours, but we use meters and seconds. 1 kilometer is equivalent to 1,000 meters since the kilo prefix means 1,000. This prefix is derived from the Greek word hili, which means 1,000. 1 hour, on the other hand, is equivalent to 3,600 seconds. But to make things easier, in this video I use both miles and kilometers per hour. But that's not all. Another key aspect about how fast things are moving is that you must also ask compared to what are they moving. Without a frame of reference, questions about speed cannot be answered completely. For example, when you measure the speed of a car, a train, a plane, or even yourself walking or running, the frame of reference is the ground. That means the earth. If we say a car is moving at a speed of 50 miles per hour, that's 80 kilometers per hour, we compare its speed relative to the ground. So the frame of reference is the ground. That's the earth. So when you think you are sitting still in your armchair, that's because the frame of reference you use is the earth. So you're not moving relative to the earth or the ground. But remember, our planet actually is moving and pretty fast, by the way. Now we'll change our frame of reference in order to find out how fast you are actually moving when sitting still comfortably in your armchair. So first let's use the Earth axis as a frame of reference and let's ask how fast does our planet rotate, or how fast are we spinning, which is the same. The Earth rotates once every 23 hours, 56 minutes, and 4 seconds around its own axis. But wait a second, isn't the day 24 hours? Astronomers calculate the day in 2 ways, so they use 2 different frames of reference. If we take as a frame of reference the background stars located far away, the amount of time it takes the Earth to complete one full rotation on its own axis is 23 hours, 56 minutes, and 4 seconds. Astronomers call this a sidereal day. However, if we use the Sun as a frame of reference, our planet makes a complete rotation around its own axis in 24 hours with respect to the Sun. So let's see why we rotate in 23 hours, 56 minutes, and 4 seconds instead of exactly 24 hours as we used to think. For example, on day 1, the Sun and a certain distant star are both overhead. Then, on day 2, the planet has rotated 360 degrees and the distant star is overhead again, but the Sun is not. We need another 3 minutes and 56 seconds to see the Sun overhead. That happens because the Earth doesn't only rotate on its own axis, but it also orbits the Sun, and as we move in our orbital plane, the position of the Sun changes. So we need another 3 minutes and 56 seconds for the Sun to return to the same spot in the sky. Since the Earth is orbiting the Sun, we actually need an extra 3 minutes and 56 seconds each day to return the Sun to the same spot in the sky. Astronomers call this a solar day and is the one we use in the Gregorian calendar. However, the Earth has already completed the 360-degree turn 3 minutes and 56 seconds ago. So, to get the actual time it takes our planet to make a full 360-degree turn, we use the distant stars as a frame of reference instead of the Sun. So now that you know the amount of time the Earth requires to complete one full rotation on its axis, let's see how fast does it rotate. Any place on Earth makes a full 360-degree rotation in 23 hours, 56 minutes, and 4 seconds, so all the places on our planet have the same angular speed. However, the speed depends on what latitude you're located at. That's because the circumference of the Earth at the equator is the largest with 24,906 miles or 40,075 kilometers, and as you travel to higher latitudes, the circumference becomes smaller. Since speed is equal to the distance traveled over the time taken to travel that distance, and since all the places on Earth have the same angular speed regardless of their latitudes, they all complete the full rotation in the same amount of time. However, due to the difference in size of their circumferences, they travel different distances in the same amount of time. So those places located closer to the equator travel longer distances, and those located in higher latitudes travel shorter distances. While a person positioned at the equator travels 24,906 miles or 40,075 kilometers in 23 hours, 56 minutes, and 4 seconds, another at the North Pole needs the same amount of time to spin in place. So if we divide the circumference of the equator by the length of the day, we get a speed at the equator of about 1,040 miles per hour or 1,675 kilometers per hour. That's about 60% faster than the average commercial plane. The speed decreases as you move north or south from the equator, but still a good clip throughout North America and Europe. If you move halfway up the globe to 45 degrees in latitude, either north or south, the rotational speed at 45 degrees is around 733 miles per hour or 1,180 kilometers per hour. That speed decreases more as you go further north or south. By the time you get to the north or south poles, your spin becomes very slow and it takes an entire day to spin in place. But that's not all. In addition to spinning on its axis, the Earth also revolves around the Sun. We are approximately 93 million miles or 150 million kilometers from the Sun, and at that distance it takes us 365 days, 5 hours, 48 minutes, and 45 seconds to complete a full orbit around the Sun. The full path of the Earth's orbit is close to 600 million miles or 940 million kilometers. So if you think you don't travel much enough, think it twice because you travel 600 million miles or 940 million kilometers around the Sun each year. That's around the same distance from the Earth to Jupiter. But listen to the following numbers. If we divide that distance by the length of the year, we get an orbital speed of about 66,000 miles per hour or 107,000 kilometers per hour. That's 18.5 miles per second or 29.7 kilometers per second. At that speed, you could circumnavigate the Earth's equator in just 22.4 minutes and cover the distance to the Moon in 4 hours. That's over 3 times the speed of the International Space Station and 2.5 times the max speed of the Apollo 11. But there is more. Our Sun is just one star among several hundred billion others that together make up the Milky Way galaxy, our bigger home. All those stars that make up the Milky Way are also moving, and among them our Sun. Since any planet orbiting a star will share its motion through the galaxy with it, that means the Earth and the entire solar system also are in motion orbiting the center of the Milky Way. The Milky Way is so big that it is around 100,000 light years across. That means that something traveling at the speed of light, the speed limit of the universe, needs 100,000 years to cross the whole galaxy. Our solar system is about halfway from the center of the galaxy. That's about 25,000 light years. So the speed at which the solar system moves around the center of the Milky Way is an astounding 483,000 miles per hour or 792,000 kilometers per hour. So we are orbiting the center of the Milky Way at the speed of 140 miles per second or 225 kilometers per second. At that speed, an object could circumnavigate the Earth's equator in just 2 minutes and 58 seconds. But the Milky Way is so vast that even at this great speed, our solar system requires about 225 million years to make one complete orbit around the center of the galaxy. This is called our galactic year. Since the Sun and the Earth first formed about 4.6 billion years ago, about 20 galactic years have passed. That means we have been around the galaxy just 20 times. Our planet is just 20 galactic years old. And by the way, we live in the same galactic year of the dinosaurs. But the universe is filled with billions of galaxies, and they are not sitting still. All of them are moving too. And that includes our galaxy, the Milky Way. For the different speeds of our planet mentioned so far, we've always used different frames of reference. In your armchair, your speed compared to the walls of your house is 0. Compared to the Earth's axis is over 700 miles per hour or 1,126 kilometers per hour. Compared to the Sun, it is about 66,000 miles per hour or 107,000 kilometers per hour. And compared to the center of the galaxy, it is about 483,000 miles per hour or 792,000 kilometers per hour. But compared to what are we measuring the motion of our galaxy as all the other galaxies are moving to? To answer this question, you have to think about the Big Bang and expansion of the universe. Since the Big Bang about 13.7 billion years ago, when the universe was born, it has been expanding. And when the universe expands, it is space itself that is stretching. Well, actually space and time, since they are the same thing, but I'll leave that for another video. The whole universe is filled with microwaves and other radio waves. They fill all of space, and as the universe is expanding, these microwaves and radio waves are expanding with it, so they always fill the universe. These waves are known as the cosmic background radiation, and as they fill the whole universe, they are everywhere, all around you. So that's the frame of reference we use to compare the motion of the Milky Way as well as of the other galaxies. The galaxies in the universe are moving apart because space stretches and creates more distance between them. So, going back to our question about how fast is the Milky Way and accordingly all of us moving through the intergalactic space, well, it turns out to be a blazing 1.3 million miles per hour or 2.1 million kilometers per hour, which is equivalent to 361 miles per second or 583 kilometers per second. At that speed, you could travel from New York City to Chicago in just 2 seconds or from New York City to London in 9 seconds. At that speed, you could circumnavigate the Earth's equator in 68 seconds. However, as fast as these numbers sound, it is just a little fraction compared to the speed of light, equivalent to 0.19% the light speed. Thus, each year we travel 11.4 billion miles or 18.3 billion kilometers. Our galaxy belongs to a cluster of nearby galaxies called the Local Group, comprising about 80 galaxies. Our galaxy, together with the rest of the galaxies of the Local Group, are moving toward the Virgo cluster, an enormous group of over 1,300 galaxies located some 59 million light-years away in the direction on the sky that is defined by the constellations of Leo and Virgo. The reasons for this motion are not fully understood. Some people think there is a huge concentration of matter in this direction and they call it the Great Attractor. This Great Attractor has a mass of 100 quadrillion times greater than our Sun and a span of 500 million light-years across, and it is probably made of both visible matter that we can see along with the dark matter that we cannot see. If you ask why we don't feel all this movement, that's because these speeds are constant. It means these speeds stay the same all the time, so we don't feel any acceleration or deceleration. You can only feel motion if your speed changes. For example, if you are in a car which is moving at a constant speed, you will not feel much motion. However, when the car accelerates or when it slows down, you feel the motion. Another example is that of an airplane flying. When the plane is traveling at a constant speed and constant altitude, you can go on walk down the aisle, but you cannot feel the movement of the plane. The reason is simple. You, the plane, and everything else inside is traveling at the same speed. In order to feel the movement, the plane must change its speed or altitude. So, the same happens with the Earth, the solar system, and the Milky Way. For example, if the Earth were to change speed, we'd certainly feel that, and it wouldn't be pleasant at all, like setting acceleration or like applying the brakes at the planetary scale, while the atmosphere would keep moving at the same speed and white the surface of the planet. Fortunately for us, nothing like that happens, and we are moving at the blazing 1.3 million miles per hour or 2.1 million kilometers per hour, and we don't feel it. So the next time someone asks you why you're sitting there all day long watching TV, you can answer, although it may look as if I'm just sitting still, I'm actually moving at a great speed through the universe. So thank you for watching this video, and if you like it and it was useful, please subscribe to my channel of Science and Exploration. Goodbye, folks!